am Sharon Elizabeth Paris, and I will be presenting the first part of our project on predicting dengue using machine learning models. My section will cover the abstract, introduction, and the literature review. Abstract. Dengue has become one of the most serious public health problems in Bangladesh, with seasonal outbreaks placing huge pressure on healthcare services. To reduce this burden, early warning systems are essential. In our study, we applied different machine learning models such as logistic regression, decision trees, and neural networks to predict dengue outbreaks using real patient data. Among the models, decision tree performed well in terms of both accuracy and interpretability, while neural networks captured more complex relationships but were less explainable. Overall, this study shows the potential of data driven systems to improve dengue prediction and strengthen healthcare responses in Bangladesh. Introduction. Predicting dengue accurately and on time is still a major challenge in Bangladesh. Frequent outbreaks not only affect patients but also put extreme pressure on hospitals and healthcare workers. To address this, we use both clinical and hematological data, such as blood test results, age, and gender, to train machine learning models that can distinguish between dengue positive and dengue negative patients. We worked with two types of datasets: the real dataset, which contains actual clinical records, and the extended dataset, which was expanded using feature engineering and imputation techniques to create more diversity. By comparing these datasets, our study explored how models perform on real world datasets versus enriched synthetic data. We applied supervised learning techniques, including assembled classifiers like random forest and AdaBoost, and evaluated them using confusion matrices, ROC curves, and other metrics. This approach helps us understand the trade-off between accuracy and practicality in real healthcare settings. Literature review. Previous research on dengue prediction started with simple demographic factors like age and gender, but more recent studies focus on hematological markers such as hemoglobin, platelet count, and white blood cell counts. This aligns with our extended dataset, which includes a wide range of laboratory features. Handling missing data has also been a key challenge. The literature shows that imputation methods such as mean, mode, or k nearest neighbors improve model performance. Our real dataset, however, kept imputation minimal to reflect the practical limitations in resource constrained environments like Bangladesh. When it comes to model selection, assemble methods like random forest and other boost consistently perform well because they handle imbalanced datasets and multicollinearity effectively. Many studies report accuracy above 80%, which supports our decision to use these models. For evaluation, researchers often use metrics such as precision, recall, F1 score, and ROC AUC to measure performance. AUC values above 0.85 are generally considered strong indicators of predictive power, especially when minimizing false negatives is critical in medical contexts. Finally, the literature highlights some gaps. While assemble methods dominate, newer approaches using deep learning and hybrid models are combined clinically. Text with lab data are emerging. Another underexplored area is temporal modeling, that is analyzing how symptoms progress over time. Also, there is a growing need for lightweight explainable models that can be used directly in hospitals for faster decision making. That concludes the abstract, introduction, and literature review. In the next section, my teammates will walk you through the methodology we applied, including data preprocessing, model training, and evaluation. Thank you.
So my part is data preprocessing. Uh, in machine learning project, the quality of the data is everything. Raw clinical data is often messy with missing values, duplicates, and irrelevant information. So our first and most critical phase was data preprocessing. Think of this as preparing our ingredients before we start cooking. So first, we followed a systematic six-step process to ensure our data was clean, complete, and ready for our models. Handles missing data via mean imputation. We noticed some blood test result like ESR, and lymphocyte were missing. Instead of throwing away those patient records, we filled the gaps using mean imputation, simply replacing the missing value with the average of that specific test result. Removing duplicates. We scanned the dataset and removed any duplicate entries to prevent our models from being biased by over-represented data. Uh, Here we can see that example after removing the duplicate. That's for real dataset and that's for extended dataset. Eliminating irrelevancy. Uh, we dropped administrative columns like serial and date. These are useful for record keeping but offer no predictive value for diagnosing dengue. This helps the model focus only on what's important. Uh, Encoding categorical variables. Machine learning models work with numbers, not words. So we converted categorical data into a numerical format. We used one hot encoding for gender to avoid creating a false ranking, and we mapped our target variable result from positive or negative to simple 1 or 0. Splitting dataset. We partitioned our data into training set 80% and a testing 20%. Crucially, we used stratified sampling. This ensures that the proportion of positive and negative cases was the same in both sets, which is vital for building an unbiased model. Feature scaling. Finally, we applied standardization. Features like platelets and age are on vastly different scales. Standardization scales them to have a mean of 0 and a standard deviation of 1. This ensures that no single features can dominate the learning process simply because uh, the numbers are larger. Then next step is the learning phase. So our chosen model was random forest, AdaBoost, and XGBoost, decision tree, Gaussian naive Bayes, and artificial neural network, NN. And powerful, a random forest and powerful model that builds a whole forest of decision trees and combines their outputs for a highly accurate prediction. AdaBoost and XGBoost, these are boosting models. They build a series of some simple models where each new one learns from the mistakes of the one and before it. XGBoost in particular is known for its exceptional performance. Decision tree classifier. A straightforward flowchart like a model that is very easy to interpret. A Gaussian naive Bayes, a fast and efficient model based on probability and Bayes theorem. Neural network, a model inspired by the human brain, which is excellent at learning complex non-linear relationship. Then, uh, model, then come from model evaluation. In model evaluation, in model evaluation, uh, we show that model evaluation, we show lots of things like confusion matrix, precision and recalls. Then so in confusion matrix, this gives us a deeper look at model's errors. It tells about true positives, true negatives, false positive. True positive dengue cases we correctly identified. True negative health cases we correctly identified. False positive the healthy people we wrongly diagnosed with dengue and mostly critically false negatives, the dengue patients that our model missed in any medical diagnosis. This is the error we want to minimize the most. Precision and recall. Precision tells us of all the patients we predicted had dengue, how many actually did. Recall or sensitivity tells us of all the patients who truly had dengue, how many did our model successfully find. For diagnostic test, a highly recall is extremely important. Then ROC curves and AOC curves. So the ROC curve shows how well a modern model can distinguish between positive and negative cases as the area under the curve. Summarize this into a single score from 0 to 1. A score of 1 is a perfect classifier. Here we can see that the uh, mm, best model that is XGBoost classifier achieved an outstanding AOC score of 0.98, indicates excellent diagnostic ability. So we can say that accuracy. Here we can see that random forest is 0.167, AdaBoost 0.916, and neural network exhibit decision tree. So this one for real data set and this one for extended data set. So in extended data set, the model performs very well. So we can see that confusion matrix between real data set and extended data set. Uh, then ROC and AOC curve, ROC and AOC curves. This is real data set and this for extended data set. So the random forest AOC exhiboost AdaBoost, and for example random forest and exhibit. This defines the real dataset and extended dataset. And the result, and we can see the result and conclusion, which will be discussed our next, which will be discussed by our next member. And lastly, I can say conclusion. In conclusion, through a systematic process of data preprocessing, comparative model training, and rigorous evaluation, we are able to develop a highly effective model for dengue prediction. And our results show that uh, random forest and XGBoost are better for this model. So thank you.
Assalamualaikum everyone. Today I will be presenting our research on developing a robust machine learning framework for early and accurate prediction of dengue fever using real world clinical data from Bangladesh. Dengue fever represents a significant public health challenge, particularly in tropical regions like Bangladesh. Traditional diagnostic methods often face limitations in terms of speed and accuracy, making early detection crucial for effective treatment and management. Here, my part is the learning phase, model training. So I will cover that part. Uh, our study mainly focuses on the model training phase, which forms the core of our predictive modeling process. During this phase, various machine learning algorithms are systematically trained on preprocessed dataset to learn underlying patterns and relationships between input features and target variables. The ultimate goal is to develop a robust function capable of accurate mapping a patient's clinical and demographic data to a dengue diagnosis, essentially determining whether a case is positive or negative for dengue fever. Methodology, classification, algorithm selection. We adopted a comparative approach using six distinct classification algorithms to ensure comprehensive evaluation of different modeling techniques. This strategy allows us to identify the most effective and suitable algorithm for this specific diagnostic task. The algorithms we implemented and compared included random forest, XGBoost, AdaBoost, decision tree, neural network, Gaussian naive Bayes, data strategy, and augmentation. One of the key challenges in medical machine learning is limited data size. To address this, we implemented a data augmentation strategy. Original dataset used as our baseline for model training. Extended dataset created through synthetic data generation to provide more diverse training examples. This approach allows our models to learn from a larger and more diverse set of examples, potentially improving their ability to distinguish between positive and negative dengue cases. Model accuracy comparison. Our results demonstrate the positive impact of data augmentation on model performance. Here are some key findings. A random forest in original dataset, the accuracy was 97.75%, and uh, in the extended version, it was 98.5%. Uh, for XGBoost in the original dataset, the accuracy we find it was 97.5%, and in the extended data set, it was 98.25%. Uh, uh, so most of the classification algorithms provide us different accuracy for original dataset and the extended dataset. Then uh, I'm going to cover the ROC curve analysis. Here the ROC curves and AOC scores validate our model's diagnostic capabilities. All models demonstrate excellent discrimination ability with AOC scores above 0.95. The curves show strong performance across different threshold settings. Random forest, and here if we see on the data tables, we can see the curves show strong performance across different threshold settings. Random forest and XGBoost consistently show superior performance on both datasets. Okay, confusion matrix insights the uh, co- okay, sorry for the high true positive and true negative rates across all models. Then minimal false positive and false negative, crucial for medical diagnosis. Consistent performance patterns between original and extended datasets. Key observations and clinical significance. This model ensemble methods superiority, random forest and XGBoost being as ensemble method consistently outperformed individual algorithms, demonstrating their effectiveness for complex medical diagnostic tasks. Data augmentation benefits. Most models showed improved accuracy with extended dataset, indicating that synthetic data generation is a valuable strategy for enhancing model robustness. Then reliability for clinical use with accuracy rates above 96% for most models. This algorithm shows strong potential for supporting clinical decision making in dengue diagnosis. Then feature importance analysis. Our analysis reveals which clinical parameters are most predictive of dengue infection. The feature importance plots show that certain biomarkers and clinical indicators consistently contribute more to accurate diagnosis. This information is valuable for uh, clinicals to focus on the most relevant diagnostic indicators. The cross validation results demonstrate that our models maintain consistent performance across different data splits, indicating model reliability and generalizability. Stable predicted performance across various patient population. Uh, the calculation and clinical impact. This project successfully developed and rigorously evaluated a machine learning framework for early and accurate prediction of dengue fever. Our findings indicate that random forest emerges as the most effective model with 98.5 accuracy on the extended dataset. Data augmentation significantly improves model performance across multiple algorithms. Ensemble methods demonstrate superior diagnostic capabilities compared to individual algorithms. The validated models represent a practical and highly accurate tool for clinical uh, decision support at healthcare facilities in Bangladesh, potentially enabling rapid data-driven dengue diagnosis and improving patient outcomes. Real-time diagnostic support systems in healthcare settings, early intervention strategies for dengue management, scalable machine learning solutions for other tropical uh, disease diagnostics. That's all from my part. Thank you for your attention. I would be very happy to answer any questions about our methodology, results, and clinical applications. Thank you.